Hey guys, today I'll be talking about latches and flip-flops. What is a latch? A latch is an electronic logic circuit that has two inputs and one output. One of the inputs is called the set input and the other is called the reset input. There are two types of latches, active high circuit latch and an active slow circuit latch. In an active high circuit latch, both the set and reset inputs are connected to the ground, or either set to zero. When the set input goes to high, which means it's set to on, the output also goes high. When the set input returns to low, however, the output remains high. The output of the active high latch stays high until the reset input goes to high. Then the output returns to low and will go high again when the set input is triggered once more. In other words, the latch remembers that the set input has been last used. The set input that has been last used, if the set input goes high for even a moment, the output goes high and stays high. Even after the set input returns to low, the output returns to low only when the reset input goes high. Active low circuit. In an active low latch, the inputs are normally held at high. When the set input momentarily goes low, the output goes high. The output then stays high until the reset input momentarily goes low. Not Q and Q bar. Latches also have a secondary output, which is simply the inverse of the first output. The output of a latch is Q, thus the second output is known as not Q or Q bar. Thus, if Q is high, then Q bar is low and vice versa. Here is an example of the same theory we were talking about. This is an active high. SR, we are here using um, NAR gates. And this is an active low. We're here using NAR gates. What is a flip-flop? A flip-flop is a basic digital memory circuit which stores one input, one bit of information. It is also known as a bistable multivibrator or a one-bit memory. These are used as memory elements in sequential circuits. The output is obtained in a sequential circuit from a combinational circuit or flip-flop or both. The state of flip-flop changes at active state of clock pulses and remains unaffected when the clock pulse is not active. Meaning, the state of the flip-flop only changes when the clock either gives a negative pulse or a positive pulse. In particular, clocked flip-flops serve as memory elements in synchronous sequential circuits, and unclocked flip-flops, basically which are latches, serve as memory elements in asynchronous sequential circuits. These are the characteristics of flip-flops and latches. A flip-flop is a bistable device that has two stable states, which are represented as 0 and 1. A latch is also a bistable device whose states are represented as 0 and 1. The output is only changed for a flip-flop when the clock signal is received or any other signal from a control signal. For a latch, output changes depending on the input. Thus, it checks the inputs continuously and changes the output according to the inputs. A flip-flop always has a clock signal. Latches do not have clock signals. A flip-flop can be built for latches, and latches are built for gates. There are three types of flip-flops. There are the JK flip-flops, T flip-flops, and the D flip-flops. The JK flip-flop. The JK flip-flop is the most versatile of the basic flip-flops. This flip-flop has two inputs labeled as J and K. If J and K are different than the output, Q takes the value of J at the next clock edge. The inputs are labeled J and K in honor of the inventor of the device, Jack Kilby. If J and K are both low, then no changes occur. If J and K are both high at the clock edge, then the output will toggle from one state to another. It can perform functions of the set and reset flip-flop and has the advantage that there are no ambiguous states. It can also act as a T flip-flop to accomplish toggling action if J and K are tied together. This toggle application finds extensive use in binary counters. The above diagram is the diagram of the JK flip-flop with NAND gates. While this implementation of the JK flip-flop with 4 NAND gates works in principle, there are problems that arise with the timing. The timing pulse must be sharp because a change in the Q before the clock pulse goes off can throw the circuit into oscillation called racing. Here's the truth table for the 9-gate JK flip-flop. When T is set to 0 and J and K are set to 0, nothing changes. It remains in its previous state. When there is no input from T, but J and K are set to 0, this resets the flip-flop. The output goes to 0 and thus the state of the flip-flop means it's in reset state. When T is 0 and J is set to 1 and K is set to 0, Q, the output is 1, thus the JK flip-flop is in its set state. When T is set to 1, J is set to 1, and K is set to 1, Q is in its previous state. Q is in its previous state and is set in its toggle mode. And T flip-flop. I'm just giving an example here. When you toggle the lick switch, you are changing from one state to another, which is on or off, and the other state, which is off or on. This is equivalent to what happens when you provide a high input to a T flip-flop. If the output is currently high, it changes to low logic. If it's currently logic low, it changes to logic high. A logic low input causes the T flip-flop to maintain its current state. Here's an example of what a T flip-flop looks like on the circuit. And here's the truth table for the T flip-flop. And finally, the D flip-flop. D flip-flops are used as part of memory storage elements and data processors as well. D flip-flops can be built using NAND gates or NOR gates. The major application of the D flip-flop are to introduce delay in the timing circuit as a buffer and sampling data at specific intervals. D flip-flop is the simpler in terms of wiring compared to JK flip-flops. Whenever the clock signal is low, the input is never going to affect the output state. The clock has to be high for the inputs to get active. Thus, the D flip-flop is controlled by stable latch where the clock signal is the control signal. Again, this gets divided into positive edge trigger D flip-flop and negative edge trigger D flip-flop. Here is an example of what a NAND gate D flip-flop looks like. And here is the truth table for such flip-flop. When D has no input, it's in its normal, D flip-flop is in its normal state, it will not change. When D has a 0 input, S has a 0 input, R has an input of 1, this puts Q at 0, giving output of 0, and this resets the state of the flip-flop. And when D is set to 1, S is set to 1, and R is set to 0, it sets Q at 1. The output of Q is 1, thus the flip-flop is in its set state. And these are latches, and the three flip-flops I talked about, the T, JK,